fourth unit. That means your fourth unit does not require the knowledge of third unit. Okay, so they are all independent only, but still they can be handled independently. That's why I just went on to went on to go with the fourth unit. I thought the college would be reopening this by the next week, but it didn't happen. So I just start with the third unit. I thought third unit can be finished directly, but the chances are very dim. So I'm going to the third unit. Third unit is, see, your third unit, fourth unit, and fifth unit, the contents are very less, and it is very easy to score with those units, with those three units. And also your third unit requires some knowledge of your BJT, some knowledge of how you worked in the BJT. Okay, that would really help for you. And I would suggest this is use this third unit to score more marks. Okay, that is what I would suggest everyone. Fine. Okay, and I'll start my lecture. See, your third unit is JFET and MOSFET amplifiers. Initially, we will start with the JFET amplifiers. MOSFET amplifiers is just a small modification. You can directly apply the MOSFET amplifiers in the place of JFET amplifiers. Okay, so I'll just start with the JFET amplifiers. So before entering into the amplifiers, FET amplifiers, we need to know what is the basic difference between the BJT and FET. Okay. So I hope, yes, any problems? Okay. So BJT and FET, if you compare the BJT and FET here, both are three terminal device, so both are transistors. But what is the basic difference between the BJT and FET? I'm sure you must have you must have studied this in very detailed manner in your first year, maybe in electronic devices or something. But still, there is something that we could recollect for this BJT versus FET. Okay, and here you can see for the BJT, the control current. So I will take the laser point. Yeah, the control current IB is going to control the BJT. Whether the transistor should remain on or off, that will be decided by the control current IB, that is a base current IB. Whereas here it is controlled by the voltage VGS, that is between the gate and the source. As you know, BJT is of collector, emitter, and base. Collector, emitter, and base. Here it is drain, source, and the middle one is gate. Here the middle one is base. Here the middle one is the gate. And here the gate current is normally it is equal to 0, and it is approximately equal to 0. It is very minimal. So we approximate that every time we will approximate that to 0. And also this device is going to be controlled by the voltage VGS. That's why BJT is known as the that's why FET is known as the current control device, and BJT is known as the voltage control device. You can easily check the current IC. If you check the current collector current IC in the BJT, is nothing but it is equal to beta into IB. Correct. So this IB is the input parameter, and IC is your output parameter. IC is your output current. Whereas here, if you see, ID is equal to, you remember Shockley's equation? I will show you that in the next slide. If you remember the Shockley's equation, ID is equal to IDSS, that is drain current is equal to drain saturation current, IDSS, drain to source saturation current, IDSS, into 1 minus VGS divided by VP, the whole square. That is your Shockley's equation. There, if you see, I'll show you in the next slide. Okay. So BJT is a current control device, and JFET is a voltage control device. That's what we are trying to prove. This is a very basic difference. And the next one is IC. IC is a function of IB, and ID, whereas your drain current in FET. Here, this is the line for BJT, and this is the line for FET. FET, in the FET, the drain current, the output current is controlled by the VGS. That's why it is a voltage control device. And here we have bipolar. It is a bipolar junction transistor because the current conduction is due to both the electrons and the holes. That's why we call that as a bipolar. That's why it is named as a bipolar. Bipolar, the word bipolar is there. Whereas if you see the FET, it is a unipolar device. The conduction will be either because of the electrons or because of the holes. If it is because of the electrons, then we call that as a n-channel JFET. If it is because of the holes, then we call that as a p-channel JFET. Okay, that's why FET is a unipolar device. The conduction, the output is solely depend on any one of the charges, either electron or hole. So whoever is unmute, please mute yourself. Okay, so these are all some of the basic differences. And so to dig a little more deep for BJT versus FET, the input impedance, if we check the input impedance of the FET, it is very high when compared to the BJT. The FET input impedance will be around 1 mega ohm to 100 mega ohms, and it is a very important characteristic in designing any linear AC amplifier circuits. Okay, so whenever we talk about amplifiers, we talk about input impedance, output impedance, and the voltage gain. Okay, these are all the three things, and FET already has that advantage of having a very high impedance with it. Okay, when compared to the BJT, and the sensitivity of BJT is very high, and whereas the FET's sensitivity is very low. This is advantageous for BJT and disadvantage for FET. At some time, FET takes the advantage of that, being insensitive to some input signal. Okay, so at that time, FET can take that advantage. Okay, sensitivity can be advantage or a disadvantage. So BJT is higher sensitive, much higher sensitive when compared to the FET. And if you check the AC voltage gains, BJT has a very high voltage gain when compared to the FET circuits, FET based circuits. Okay, that is that is one more advantage because FET also has a voltage gain, but not as close to BJT. But still, FET's voltage gain is enough to manage the electronic appliances so far we are handling. Okay, so FET is more advantageous than BJT. Okay, even though BJT has a higher voltage gain. Okay, and FET is more temperature stable, and whereas BJT is not highly stable with the temperature, because in the BJT we have that problem of thermal runaway. This thermal runaway is because because of the collector current. We have already seen that you already had a 1 mark or 2 mark question in your CT1. You know about that runaway problem is very minimal in FET, so it is more temperature stable, and BJT is more more vulnerable to the temperature. Okay, and also FETs are very small in size, so that it can be easily put into the integrated circuits. Okay, fine. Okay, now we will move on to the, see, our concentration is solely on FET, so FET is the protagonist here. Okay, so these are all the types of FETs. One is JFET, that is junction field effect transistor. The word field effect is because of the fact that the movement of the charges inside the device, JFET device, will create an electric field. That electric field will control the output parameter. That's why it is known as a field effect transistor. Okay, don't ever get confused with that particular term. I'm sure you must have gone through these things. Like things too. Okay, so the JFET can be either N-channel JFET if electrons are solely responsible for the conduction of the current, and P-channel JFET if the holes are responsible for the conduction. And MOSFET, metal oxide semiconductor field effect transistor. These MOSFETs are break down to two things only. One is depletion type MOSFET, and another one is enhancement type MOSFET. And the last one is metal semiconductor field effect transistor. MESFET. Okay, these are all the FETs that is being, these are all the classification of the FETs. And right now we are going to look at JFET, and most of the circuits we are going to deal with is a N-channel JFET. Okay, so see the symbols of that JFET. First one is N-channel JFET. You can see here this is the gate. In the gate you have the arrow. Okay, if this arrow is towards that transistor, this arrow, if the arrow, that is actually the flow of current. Okay, so in BJT you will be having the arrow in the emitter that can be either pointing outside or pointing inside. That actually is for emitter current. Here it is this terminal gate is having the arrow, so that is the only difference. And also here, the line is not slant, it is 90 degree. You can upper terminal is drain and the lower terminal is the source. Direction of that arrow changes. Okay, and the direction of the drain current is also changes. The drain current will start flowing from the source to drain. Okay, that is about the P channel JFET. Okay, fine. Now hope you remember this curve, transfer and drain characteristics. You must have studied this transfer and drain characteristic curve for sure. Just go and check if not. Okay, we will be plotting this. The one half of the plot is the transfer characteristic. That is, the left half is the transfer characteristic, and the right half is the drain characteristics. In the left half of the characteristic, we have VGS here. Take it. Okay, here we have VGS in the x-axis, but in the y-axis we have ID, that is the drain current for both the transfer and the drain characteristics. Here in the x-axis we have VDS. Okay, so this is the basic difference between the transfer and the drain characteristics, and mostly we will be using the transfer characteristics for the discussion that is going to be happening now. Okay, here you can see that this curve is due to the Shockley's equation. I will show you the Shockley's equation. It is very simple, and hope you remember the Shockley's equation very well that way. Okay, fine. And also the drain characteristics, if you see, for the VGS value is fixed. Here the VGS values are fixed, and we will be changing the VDS, and we will be observing what is the drain current that can be what is the drain current that is being flowing for every value of the VDS. Okay, this is the drain characteristics. And this part is the transfer characteristics. Okay, so this is about the transfer and the drain characteristics. We will see further in detail in the coming slides. Okay, so for the DC analysis of FET amplifier, some of the things that we have to consider are, first is the gate current will be equal to 0. This is due to the high input impedance. Okay, when we have the high input impedance, only the voltage drop will be there, and consider the input impedance is infinity. The voltage drop will be there, but the current passing through that open terminal is 0. Okay, so that is the reason IG is approximated every time the gate current is approximated to 0. Okay, and here we can see the drain to source current. The drain current is almost equal to the source current. This is almost similar to what we have seen in the BJT. In the BJT, we say IC is approximately equal to the collector current is approximately equal to the emitter current. In the same way, here in the BJT, we say the drain current is equal to the source current. Okay, and this is the Shockley's equation. Okay, this is the very important equation. Okay, all you have to do is remember this. Okay, here I will explain every term. ID is the drain current, IDSS is the drain to source saturation current. Saturation, that is a maximum current that it can reach, and VGS is the gate to source voltage. That is the only variable thing here. VGS is the only variable thing here, and VP is the pinch off voltage. This is a constant. this is a constant and this is also a constant. Okay, so in this equation, I'll remove this better. Okay, so in this equation, we have the relationship between the input and the output parameters. One is ID is the output parameter and VGS is the control voltage. That's why it is known as a voltage control device. Okay, voltage control device. Whereas in the BJT we have IC is equal to beta into IB, where IC is the output current and it is controlled by the IB. That's why it is known as the current control device. Okay, and and we can see that this is for this JFET, this Shockley's equation what we have discussed is for the JFET and the depletion type MOSFET and MESFETs. Okay, whereas for the enhancement type MOSFETs and MESFETs, the ID is different, where K is a constant. Here VGS is the gate to source voltage as usual, and the VT is a threshold voltage. Okay, so every here there is a square for both. Okay, remember that, and we will move on to the next slide. This equation plays a key role throughout this discussion. Okay, just remember that. Okay. See, what are all the merits we have seen for the FET versus BJT? That is according to the device. So that device merits will be reflected in the amplifier system. So these are all some of the merits of the JFET amplifiers on comparing with the BJT. Okay. See, FET has an excellent voltage gain, but still it is less than BJT. The voltage gain is less than BJT. Okay, and higher input impedance compared with BJT. And in the previous, while discussing the feedback amplifiers, I said why we require a very high impedance for an amplifier, for designing an amplifier. Okay, so very high impedance is required for designing an amplifier. Okay, so FET has that very high input impedance when compared with the BJT, and the output impedance value, both it is comparable with the BJT. Actually, FET and BJT almost have the same output impedance. Okay, output impedance value should be as low as possible. Still, BJT competes with FET there, and it consumes very low power. It has a very good frequency range. It means that the bandwidth can be very high. Okay, it means the very good frequency range means the frequency operation is linear over a large number of frequencies. Okay, the bandwidth can be very high in the FET. Okay, and also it is a minimal size and weight. It is of minimal size and weight, and you can clearly see that depletion type MOSFET has much higher input than the similar JFET configuration. If I am removing that JFET from that amplifier and I am plugging in that depletion type MOSFET, it has a better higher input impedance than the JFET. Okay, that's what they are trying to say. But still, we are restricting our discussion only to the JFET right now. MOSFET will be discussed later. It is a very simple one. Okay, fine. When a small AC voltage is applied to the input gate to source terminal, that will actually control the current that is flowing from the drain to source. Okay, that is actually given by the drain current IDSS. That is a Shockley's equation. This equation will be keep on following you. So just remember this equation. You can answer a hell a lot of questions with this equation, with this one equation. Okay, and the change in the drain current, is because of the change in the VGS. Change in the VGS means the change in the gate to source voltage that is being applied. That change in the VGS will directly reflect in the change in the drain to source current. Okay, and it is determined, and this can be determined by the transconductance value here, GM. GM is the transconductance factor. Okay, if you check this transconductance, this term transconductance, trans means the relationship between the transfer characteristics, say transfer function, output and input. Trans means it is a relation between the output and the input, and the conductance is the inverse of the resistance. That's why we have for the resistance we have R is equal to V by I, R is equal to V by I. Whereas for the resistance, for the conductance, it is exactly the opposite. It is I by V. That's why GM is equal to del of ID divided by del of VGS. Del means nothing but a small change in the drain current, small change in the VGS. Okay, this equation actually explains that. So to put it in a form, in a graphical way, just go through your transfer characteristics of your device. This transfer characteristics, this curve here is drawn by using the Shockley's equation. If you go to the Shockley's equation here, if I substitute for VGS, in the place of VGS, if I substitute 0, I have ID is equal to IDSS. Whereas if I substitute VGS is equal to VP in this equation, we have ID is equal to 0. If I substitute VGS is equal to VP here, VGS is equal to VP here, then ID is equal to 0. Correct? Because VGS, if I substitute, you see, if I write it better. Okay, this is the equation of concern. Okay, for VGS is equal to 0, for VGS is equal to 0, we have ID is equal to IDSS. For VGS is equal to VP, we have ID is equal to 0, because when I put VP here, when I put VP in the place of VGS, VP will get cancelled, and we will be having 1 minus 1 will be 0. That's why ID will be equal to 0. And in between, if we put some value of VGS here, that means if I put VGS is equal to VP by 2. If we put VGS is equal to VP by 2, then just check that value. ID will be equal to IDSS divided by 4. Okay. I'm trying my best to write it as neatly as possible. Okay. So these are all the 3 points. With these 3 points, you just take the coordinates of these points. One is 0, IDSS. Another one is VP, 0. Okay. The third point is VP by 2, IDSS by 4. You just take these 3 points and plot it here. You just check these points. You just check these points here. First point is, for VGS is equal to 0, we have ID is equal to IDSS. For VGS is equal to 0. Okay, these are all the 2 points. And in between, when VGS is equal to VP by 2, I am taking here. Okay, then ID is equal to IDSS divided by 4. Okay, you just check this values. Okay, you just substitute the values of VGS, different values of VGS in this equation, and get the values of ID and plot it in the VGS versus ID plot. Okay, so in that you just pick an operating point, and draw a slope here. Okay, a triangle here. I will remove this marking. So when we just calculate the slope at the Q point, okay, by drawing a tangent to the curve, we will get that value of the transconductance GM. Okay, this GM is nothing but del y by del x. That is the slope, right? Dy by dx is equal to the slope. So GM is equal to del y by del x. Del y is nothing but your y-axis. That means del of ID, and del x is del of VGS. Okay, that's why we have GM is equal to del of ID divided by del of VGS. Okay. Particularly a tangent should be drawn across that Q point. Okay, by having that Q point, we will draw the tangent, and we will be getting the corresponding slope of that and finally we will be getting the actual expression for the transconductance. Okay, moving on to the mathematical model of it, just check the graphical procedure. If I see, there are some you may need in the fit biasing. I'll give that to you as an assignment. Okay, the whatever we have seen now is a graphical procedure, because across the curve we are drawing a tangent and we are finding the slope there. That is a graphical way of solving the value of GM. Whereas if I am taking another alternative approach, that is the mathematical approach of it, okay, then it would be it would be like we have to take the direct slope del id. The slope is nothing but del id divided by del of VGS. That means differentiation of id, that is differentiation of drain current with respect to the differentiation of with respect to VGS. Okay, differentiation of change in the drain current due to the change in the VGS. Okay, that is what we have to find. That is what we have to find. This is a graphical way, and the alternate approach is the mathematical way. Directly take the Chocolate's equation, id is equal to IDSS into 1 minus VGS by VP the whole square, and differentiate it with respect to VGS. Okay, these are all the differentiation steps. I just took directly from the book because it is very clear here. We can clearly see that since VGS 1 minus VGS by VP the whole square is here, we will be taking the 2 here, and on differentiating we will be ending up with GM is equal to 2 into magnitude of VP. Here you should notice that it is given as magnitude of VP, because here it is minus of VP. See, the outcome of this will be a negative value as well, but the transconductance value should be always positive. So that's why this VP is taken the mod of VP is given here. Okay, that's what that's what it is mentioned here, where the magnitude of VP denotes will make sure that the value of GM will be always positive. Okay, and the parameter 1 minus VGS by VP will be always lesser than 1. Okay. Okay. So, so at VGS is equal to 0, the above equation, the previous equation we have derived, that can be again written as when VGS is equal to 0, the slope will be maximum. Okay, when VGS is equal to 0, the slope will be maximum. That's why we call that as a GM 0. This 0 means VGS value is equal to 0. That's why the corresponding slope GM is represented. 0 is nothing but when I substitute VGS is equal to 0 in the equation we obtained for GM, we put VGS is equal to 0. Okay, then we will be having GM 0 as 2 into IDSS into VP. Now the slope GM can be written as GM into GM naught, because the term that is given here is replaced with the term that is given here. This term is being replaced with GM 0. Okay, fine. Okay, now we will see the plots for this transconductance, how the transconductance varies with VGS, how the transconductance varies with the ID. To give you an idea of the transconductance as a function of VGS and as a function of ID. First, transconductance as a function of VGS. This is a direct equation. This is the equation we have discussed before. Just take that, plot, vary the value of VGS, and plot the values of GM in y-axis. We will be having the curve like this. We can clearly see that when VGS is equal to 0, when I put VGS is equal to 0, GM, when I put VGS is equal to 0, I will get GM naught, that is a maximum value. Okay, and when we put VGS is equal to VP, then GM will be equal to GM will be equal to 0. That's why we have only VP here. Okay, and then I remove that. Okay, and second plot is ID versus VGM. See, generally this GM and ID don't have a direct relationship. Okay, GM and VGS, that equation is directly related with VGS, luckily, but not in all the cases. GM will be equal to GM will be a function of ID. Okay, that's why we are modifying using the Shockley equation. From the Shockley equation, we can write ID is equal to IDSS into 1 minus VGS the whole VGS by VP the whole square. That equation is modified like this because we are taking we are taking both sides, taking the IDSS down here. Here the IDSS is taken down, and ID is here. Taking the square root on both sides, we have the term 1 minus VGS by VP. This 1 minus VGS by VP is replaced. I'll show you. This 1 minus VGS by VP is replaced in this equation of GM. Then we will be getting the final equation as GM is equal to GM0 into root of ID divided by IDSS. Okay. Now GM is represented as a function of drain current. Okay. Now we will straight away go for the plot. If I put ID is equal to 0, then GM is equal to 0. If you put ID is equal to IDSS by 4, then we will be having the corresponding value of GM there. So it is almost linearly increasing there. Okay. So and ID cannot go beyond the IDSS. That is the saturation current. Okay, drain to source saturation current. That's why this curve stops here. Fine. Okay, so this is the, and it should be noted that the value of GM, that is the transconductance, the unit of that is S means Siemens. Okay, fine. So we'll move on to the next slide. JFET input and the output impedance. The JFET input impedance is obviously it is very high input impedance. So ideally we will be taking that as an infinity ohm. Okay, but if we just check, it will be around 1000 megaohm. Okay, which is very high. 10 power 9 ohms actually. Okay, 10 power 9 ohms for JFET, and for MOSFET or MESFET it is around 10 power 12 to 10 to 20 power 15. So it is very, very high impedance. Input impedance is very high. That's why we just approximated that to infinity ohms. And the output impedance is we can take those values from the specification sheets. In the specification sheet, we should observe that the output impedance is not directly given as Z0. Okay, instead it will be given as GOS or YOS, where GOS or YOS is output. O means output, S means source. Okay, output source. What is the transconductance, or the Y means the admittance. Okay, this GOS value typically varies from 10 microsiemens to 50 microsiemens, and when I convert this equivalent to a equivalent output impedance, then it will be 20 kilo ohm to 100 kilo ohms. Okay, so remove this. So this is the output impedance of JFET, and it is given by RD Z0 of JFET is equal to small RD. This is being this representation is being used for AC analysis, and output impedance is equal to 1 by GOS. When I substitute 10 microsiemens here, I'll be getting 100 kilo ohms. I'll be getting 100 kilo ohms. When I substitute 50 microsiemens in the place of GOS, I'll be getting 20 kilo ohms. So that's why the value of Z0 will be varying from 20 kilo ohms to 100 kilo ohms. Okay, I'll move on to the next slide. So here we have discussed about the JFET input and the output impedance. That is, this is for the device. Remember, this is for just for the device. We haven't entered into the amplifier set. Okay, fine. So JFET output impedance, that RD is nothing but the slope of the drain characteristics. You just take the drain characteristic curve and you compute the slope at the Q point. At the Q point, you just compute the slope. The variation of the del VDS is very high, very high, but very small drain current output will be there. Okay, that's why we have RD is equal to del VDS divided by del IDS. Okay, here it is not the slope, it is the inverse of the slope. RD is the inverse of the slope because slope is dy by dx. Here it is dx by dy. Okay, that's why it is the inverse of the slope. And you just draw a line around that Q point, draw the line around the Q point, and correspondingly you draw a ID for the corresponding line. So take the length of those two lines and you substitute in the place of RD to get the value of RD. Okay, that is the output impedance. Okay. So now we are entering into the very crucial part, JFET AC equivalent circuit. Okay, so JFET AC equivalent circuit, we have seen three different types of circuits for BJT. One is hybrid pi, another one is hybrid pi, RE model, hybrid pi model, RE model, and what is the one more model we have? RE model, hybrid pi model. I don't remember that. Okay, hybrid model. I think only the hybrid model, hybrid pi model, and the hybrid model. Fine. Okay, here we have only one equivalent circuit we are going to discuss. This is that equivalent circuit, and the justification for each and every parameter will be given in the given now. First, we will see why that GM into VGS comes into the picture. GM into VGS is nothing but the drain current ID, and this drain current is actually controlled by the VGS, that is the gate to source voltage. Okay, and this is not only controlled by the VGS, but it is also depends on the transconductance value GM. Okay, that's why ID is represented as GM into VGS. Okay, ID I small d, here you should see that the representation is small d and small gs in the V suffix here, because this is, we are going into the AC equivalent circuit. Okay, we have to be careful with that. Okay? In the representations are very important. You can't just keep on putting different notations for everything, because AC, once we are entering into the AC analysis, you should use the small letters only there. Okay, fine. Yes. Okay. The next one is you can see that the arrow is downward. The arrow is downward here in this. The current direction arrow is downward here. This is to make sure there is a 180-degree phase shift in the output. Okay, that is the actual behavior of the FET. That is the actual behavior of the FET. So in the equivalent model, we try to replicate whatever that is actually happening in the FET through the voltage dependent current source or the current dependent voltage source something. Okay, so we are making that arrow downward to have a 180-degree phase shift. That means the output is being inverted. Okay, and finally we have the input impedance. Input impedance is generally very high. That's why we just left it as open circuited. Here we can see there is no resistor here, no resistor, nothing is here. Okay, and it is left as open circuited. The last one is the output impedance. Output impedance we have discussed enough. This output impedance is RD, and we have discussed enough in the previous slides. Okay, so this is the AC equivalent circuit. This is the JFET AC equivalent circuit. We are going to directly substitute this AC equivalent circuit in the circuits we are going to see right now. Okay, this is the same thing we have done in the BJT. So it is very simple as well. Okay, just pay some attention. Okay. So for the AC analysis, what we do for the AC analysis of the circuit, first we will be short circuiting the capacitor, because as we know that susceptance XC is inversely proportional to 1/2, inversely proportional to the frequency. So it is very small for the AC analysis. XC will be very small for the AC analysis. That's why we just short circuit the capacitor for the AC analysis. For the DC analysis, we open circuit the capacitor. Okay, that is the difference between them. Okay, next one is short circuit the DC sources. Okay, that means remove all the DC sources. Okay, directly connect the DC source to the ground, or you just go and check your, just check with the circuit. We will be directly connecting the DC source with the ground. We will be shorting that DC source as like we are doing it that for a capacitor. Okay, in the AC analysis, that's what these steps are the same. You just have to smartly apply those steps. Okay, and the third one is replace that JFET, whatever AC equivalent circuit we have seen now. You just replace that AC equivalent circuit in that JFET. Okay, and finally start the analysis to find the input impedance, output impedance, and the voltage. Okay, fine. Okay, so this is about the AC analysis. We will apply these 4 steps. We will apply this 4 steps in the coming circuits we are going to discuss. Okay, so the first circuit is fixed bias circuit. Okay, so this is the fixed bias circuit. This is the fixed bias circuit. Here we can see the value of the VGE, that is the gate, the negative voltage that is being connected to the gate is fixed. That's why we call that as a fixed bias configuration, fixed biasing. And firstly, we will be first thing we will be doing for the AC analysis is short circuit the capacitors, and this C1 and C2 capacitor, as we have already discussed this in the class, C1 and C2 are known as the coupling capacitances. And to prevent the DC component that is coming from the input to the circuit, we connect C1, and to prevent the DC component that is being entering from the output to the circuit, we prevent that with the coupling capacitor C2. Apart from that, there is a bypass capacitor. Right now it is not there, so we don't have to confuse with that. Fine. Okay. So we have only 2 resistors. Have that in mind. We have N channel JFET here, and we have only 2 resistors here and 1 voltage source connected to the gate. That is the negative voltage source. Okay. I'm just removing the ink here. Okay. And as we know that the levels of GM and RD are taken directly from the data sheets. Okay. And I hope you remember that I have mentioned in the previous slides. So we are straight away entering into the AC analysis. For the AC analysis, first we will be short circuiting this. We will be short circuiting the capacitor. Then we will be short circuiting the gate voltage, that is the voltage that has been connected to the gate. And also there is a VDD there. In BJT we have VCC, since it is connected to the collector there. Here it is connected to the drain. That's why we represent that as VDD. And this is also should be also be grounded. Okay, or you just connect it to the ground here. Okay, these things should be, capacitor should be replaced by the short circuit. Okay, so this one, here you can see, VG circuited, and XC1, that is the capacitor C1 is short circuited, capacitor C2 is short circuited, and finally we replace the JFET with the equivalent AC circuit. Okay, you have to make sure you have the proper terminals connected to the proper resistors. And to be more clear, gate is connected with RG, and gate terminal is connected with RG, and RG resistor is grounded, and RD is connected with the drain terminal, and that too will be also grounded. Okay, so we can clearly see that the next slide. RD is grounded. Okay, RG is grounded. So within this we have the AC equivalent circuit for in the place of JFET. Okay, so now we can start our analysis. So right now the 3 grounds are different, so we are making that to a single ground for simplification, because all are in the same potential of 0. So we are redrawing this circuit as this. Okay, this is the redrawn circuit of the above circuit. Okay, First let us find the input impedance. Okay, that is the same circuit. I'm just putting the same circuit in the next slide so that our analysis will be very easy. Yes, I would like to take up some questions. Yes, those who are very much busy with putting the attendance, can you enter your number now so that I can notice who are all active now, and I will take that as an attendance. 09 27 36 24 9 27 36 17 6 15 23. Nice. Go on. Yes, guys, very good. And also, I would like to know whether you have any doubts or not, because we have went a long way. If you have any doubts, just unmute yourself and ask your doubts. Yes, any doubts? Can I go ahead? Because I am keep on discussing. You somewhere you must have some doubts. Make sure it gets clear now. Yes. Meanwhile, I will notice the attendance. Yes. Okay. I think proxy is not possible here. So yes. Yes. Anyone? Anyone having a doubt? Yes. Pragati? Okay. Okay. I will move on to the class. Okay. Now we are going to derive the input impedance, output impedance, and the voltage gain. Okay, as simple as that. Okay, firstly the input impedance. We just check the input impedance. You're just looking from here. The input impedance, it has only one resistance RG, so Zeta is equal to RG. Straightforward. Okay, so we are not involving anything here. Nothing, no other resistors are involved here. You can see this part is completely away from the input impedance part. So input impedance is very direct. We can see Zeta is equal to RG. Next we will be having the output impedance. For having the output impedance, the first point is make that VA is equal to 0. Okay, so if we make this, if we make VA is equal to 0, then this one will be short circuited, and this in turn will short circuit. If we replace this effectively with the resistor, then this will be also short circuited, and the voltage drop across this short circuit is 0 volt. So VGS will be equal to 0. Here we can see the VGS here in the AC equivalent circuit. VGS will be there, and VGS is equal to 0. Because of VGS is equal to 0, this one here, GM into VGS, that will be also equal to 0. So ultimately, we have an equivalent circuit like this. Okay, we have an equivalent circuit like this. Okay, it has only two resistors, RD and small RD and capital RD. Small RD is the output impedance of the FET. Capital RD is the drain resistance, the resistance that is connected to the drain. And with this, we can say Z0 is equal to RD parallel with small RD parallel with capital RD. Okay. I think I will repeat anyway. Okay. So for finding the output impedance, make VI is equal to 0. This is a universal for everything everywhere. We will put VI is equal to 0 for finding the output impedance, because we don't want to include the output while finding output impedance. And because VI is equal to 0, this becomes short circuited, and because of this short circuit, VGS will be equal to 0, because the overall is, and again effective resistance is again a short circuit, so VGS is equal to 0. Because of that, GM into VGS here, this is also equal to 0. Okay, and finally we have a circuit like this. Okay. So finally, we have the output impedances small RD parallel with capital RD. Okay. If small RD is usually very higher value when compared to the capital RD. So generally, since it is a parallel connection, RD and small RD and capital RD in the parallel connection, we will consider whichever is having the lower value. Okay, and capital RD will usually have the lower value, so the output impedance is capital RD. Okay, finally we have to find the voltage gain. Voltage gain is nothing but output voltage by input voltage. Okay, firstly we will find the output voltage, and we will find separately the output voltage and the input voltage, substitute it there. Okay, first one is we will be applying the we know that V0 is nothing but V0 is here. V0, if you check, we will be connecting a multimeter here to find the V0. Okay, across this. That means the voltage drop across the effective resistance of this, or we can say that the voltage drop across these 2 points. Okay, the effective resistance is small RD parallel with the capital RD, and the current through this circuit is, if I am converting this circuit, I will be having only the voltage source, the current source, and one resistor, that is RD parallel with capital RD. So through this, the current that is GM into VGS. That's why we claim that V0 is equal to minus GM into VGS, minus sign, because the output current direction is different from the GM into VGS direction. That's why we have the minus GM into VGS here, and parallel with and it is multiplied with RD into capital RD parallel with small RD. Okay, and directly we can say that VA is equal to VGS, because VGS has been directly applied here. If we just apply, consider VA is been flowing here. VA is the voltage across this resistor RG, and if you apply the KVL here, we will know that VA is equal to VA minus VGS is equal to 0. So VA is equal to VGS. Okay. So way we can find the output in the input voltage. So substitute that in the voltage gain equation. Finally, we have the voltage gain as minus GM into RD parallel, capital RD parallel with small RD. Okay, this is about the fixed bias configuration. See, I repeat, this particular derivation is enough to find the input and the output impedance of the other circuits to follow. Okay, so we will be having the same AC equivalent circuit. So we don't have to remember anything here. Just apply the logic and get the final expressions. Okay, and moving on to the next slide. Also here, if we substitute that RD is very higher, so AV, that is the voltage gain AV, can be approximated to minus GM into capital RD, because RD is parallel with small RD is parallel with capital RD. So consider whichever value is small. RD, capital RD is very small, so consider that. Okay, fine. Okay. And also you have to notice about the negative sign. This negative sign we have already seen in the RC coupled amplifier. Okay, so the same thing we are having here. Okay, the negative sign will be there in the every derivation. Okay, for the voltage gain. Okay, that means the input and the output are out of phase by 180 degree, has a phase shift of 180 degree. Okay, fine. And moving on to the next circuit, that is the self bias circuit. First one is the fixed bias circuit. The next one is the self bias circuit. Okay, the self bias circuit is actually a improvised version of the fixed bias circuit. Okay, in the fixed bias circuit, if you just check the fixed bias circuit, if you just check this fixed bias circuit, we don't have a resistor here in the source terminal. We don't have a resistor, and also we have a voltage source here, and because of this this voltage source is there, we are additionally wasting a voltage source there. Okay, by eliminating this voltage source, we could actually go for a we could actually get the self biased circuit. Okay, I'll show you the self biased circuit here. This is the self bias circuit. The only thing is we have a we don't have a voltage source here. We have eliminated that. That means we don't require two different voltage sources. Only one voltage source, VDD, will do it. VDD will do the work for us, and we don't need VGG. And also for the compensation, we are connecting a resistor RS, and across this we are connecting a bypass capacitor CS. Okay, so this is something. This is the basic difference between the uh, fixed bias circuit and the self bias circuit. And it is why it is known as a self bias circuit is that when we do the DC analysis, the voltage source VGG that is being given in the fixed bias, that effect will be actually given by the source resistance, the resistance that is connected to the source. Okay, so that's why it is biasing itself. That's why it is known as the self bias circuit. It biases itself with that source resistance. That's why it is known as the self bias circuit. Okay, you can see that self bias configuration eliminates the need of two DC supplies. Previously we had two DC supply, VDD and VGG. Here we have only one DC supply, VDD. Okay, the controlling gate to source voltage, that is this voltage plus minus VGS. VGS is actually controlled by the now it is actually controlled by the resistor RS and the voltage drop across it. Okay, and this CS, the so whoever is unmute, please mute yourself. Yes, this CS is the capacitor CS is actually open circuited for a DC analysis and short circuited for the AC analysis. Okay, this CS will definitely have an impact on the voltage gain. That also we will be discussing in the coming slides. Okay, so first thing, we have to draw the AC equivalent circuit for this one. Okay, for that we want to short circuit the capacitances first. This capacitance is also short circuited. So effectively this RS and the short circuit will go to the null, and that means it is replaced by a short circuit. So we can draw this. We can draw that like this. Here you can clearly see that the capacitances C1, coupling capacitances C1, C2 are short circuited, and also the bypass capacitance is also short circuited. Okay, and also we have replaced the AC equivalent circuit of the JFET. Okay, and you can check this circuit. Just check this circuit. This circuit is same as your fixed bias circuit. Okay, I just go bias circuit. Parallel bias circuit is same as the fixed bias circuit. That means the AC equivalent circuit are equal for both the self bias and the self bias and the fixed bias. Okay, so we are going to repeat that derivation of input impedance and output impedance and the voltage gain, literally. Okay, going back. See, this is the equivalent. This is the AC equivalent circuit for fixed bias circuit. The same circuit is being repeated for the self bias circuit. So the input impedance, output impedance, everything will be the same. The same logic supplied, no difference, nothing ditto. You just take that, you just write the same thing here, no difference, because I did the same copying and pasting it here. Okay, fine. The self bias and the fixed bias are over. All you have to remember is why we are coming to self bias and the fixed bias and the self bias circuits. That's all. It has some minor modifications only. Okay, fine. Next one is the problem is we want to show the difference. Yeah, we want to show the difference. What happens if this CS, the capacitor CS, is not connected to the circuit? Okay, that is something we have to notice here. That is the unbypassed RS. We are bypassing the signal. We are bypassing the signal in AC analysis. In the AC analysis, if we assume that the CS is not there, means then this RS will be literally coming there. Okay, so my circuit now looks like this. Okay, previously it was only the RS is not there. That's why it has been directly connected here. And also for simplicity, we are making the RD here as infinity ohms. Okay, RD is infinity ohms. Output impedance is infinity ohms because it is comparatively very higher when we compare to the value of RD. Okay, and we can say that input impedance is direct, okay, because this input is completely disconnected from this circuit. So input impedance is direct. For the output impedance, first we want to make the VA is 0. And because of making the VA is 0, what are all the effects that will be reflected in the circuit? That's what we are going to notice. Okay, for the output impedances, VA is equal to 0. That means okay, VA is equal to 0 means this is short circuited, and effectively this can be replaced by a short circuit. That means the plus of VGS is coming here. Now we have minus plus VGS, the voltage VGS here. Okay. Now we are going to carry on that analysis. Okay. Fine. On making V is equal to 0, the ground terminal is directly, and that is the gate terminal will be directly grounded. That means the VGS will be directly appearing across the resistor RS, and you can keep on noticing here. Okay, this VGS, the positive terminal of the VGS will be directly connected to the ground. That means VGS will be flowing across here. So when I apply, when we apply the what is the when we apply the KCL here in this node, in the node I am just pointing here, in the node I am just pointing here with the laser pointer, we can see that the incoming currents is equal to the outgoing currents. Outgoing current is GM into VGS, okay, and the incoming current is ID and I naught. So we have VGS is equal to minus ID plus I naught into RS. Okay, so similarly, by applying the KCL, in the you can clearly see by applying the KCL we are obtaining the two equations for VGS. One is to VGS, the input and the output input current is the incoming current is ID plus I naught, and the outgoing current is GM into VGS. Here the current that is being flowing through this resistor is resistor RS is ID plus I naught. So VGS is of opposite polarity. If you see, the negative terminal of the VGS is here and the positive terminal is connected here. After grounding the gate source, the positive terminal will be here. That's why VGS is equal to minus ID plus I naught into RS. Okay. Now substituting this VGS in this. Now substituting this VGS in this equation, we have ID plus I naught is equal to minus GM into ID plus I naught to RS. Okay. On doing all those circuits, bring ID to one side and ID naught to another side. ID to one side and ID naught to another side. We get the final expression we get is ID is equal to I naught is equal to negative of the drain current. Okay. That means what does that mean? This GM into VGS is equal to 0. Correct? Because from this relation, we can see if I put I naught is equal to minus ID here in this equation, we get GM into VGS. Okay, so that is the conclusion, and therefore we get that output voltage as minus ID into RD. Okay, and finally the output impedance is obtained by output voltage divided by the output current, which is nothing but only the resistance RD. Okay, so these are all the steps that has to be followed for deriving the output impedance, and you can't directly just write RD for the output impedance. Without these steps, I will put only 0. Okay, so you have to make sure that you get the final answer through proper process. Okay, fine. Now voltage gain is the remaining one. Okay, for voltage gain, we need output voltage by input voltage. Output voltage and the input voltage. Firstly, the output voltage, if you see, so if we just check this GM into VGS is been flowing through this resistor RD. So the voltage drop across this RD is nothing but the voltage across this RD is V output. So we have RD into GM into VGS as output voltage. Okay, and the input voltage, for the input voltage, the voltage drop across the RG resistance RG is the input voltage. VI, here this input voltage is VI, so I am just applying the KVL here, so that we will be having VI minus VGS minus VRS. VR suffix S, V suffix R suffix S. That means the voltage drop across RS. This voltage drop across RS, if you just check, it is nothing but GM into, that is the current that is flowing through this RS is GM into VGS. So I am replacing VRS with GM into VGS into RS. So finally we get VI is equal to VGS plus GM into VGS into RS, and V0 is equal to minus GM into VGS into RD. So we get the voltage gain as minus GM RD divided by 1 plus GM into RS. Now we want to compare, this is for unbypassed RS. That means if the capacitor is not connected, the bypass capacitor is not connected to the self-bias circuit. Okay. So what happens when the bypass capacitor is connected to the circuit? That's what we have derived in the previous slide. Yeah, I think this is the one. If you just compare this here, AV is nothing but minus GM into RD. If we compare, this is the bypassed one, and when we compare the voltage gain with the unbypassed system, we have lesser one, because we have the denominator of 1 plus GM into RS here. So naturally, the voltage gain of the self-bias configuration circuit, where the RS is unbypassed, the gain is lesser when compared with the self-bias configuration when the RS is bypassed. Okay, so this is the little inference that we make from this derivation. Okay, fine. I think someone wants to get clear with any doubts. I will discuss a final one. Final one is the straightforward one. There is nothing much different with the whatever things we have discussed so far. The only thing is in the place of in the place of in the place of the place of self bias configuration. Yes. In the self bias configuration, if we I'm going to end this lecture. Just a simple modification. You can remember that easily. Okay. Okay. Here, in the place of the gate resistance, if I am replacing with two different resistances, R1 and R2, that is the voltage divider configuration. Okay. This is R1 and this is R2, voltage divider biasing configuration, and we can directly check. We will directly go there now. Okay, so this is the voltage divider biasing configuration. Here you can see the RG is now separated between now it is separated as two resistances, replaced with two different resistances, R1 and R2, and this gives the voltage divider configuration. And the same thing we have to do whatever things we have done for the self bias circuit. We have to do the same thing. The only difference that will be having here is the input impedance. Previously it was Zi is equal to Rg, but here it was R1 parallel with R2. Okay, the right side you can just check the text are appearing. The input impedance is R1 parallel to R2. Okay, that is the only difference we will be getting. And the output impedance and all the same derivation we have to follow there. Okay, there is no difference, nothing. Okay, so output impedance and the voltage gain is also the same. Okay, so with this, I am ending my lecture. Okay, so I'll be available to take up some doubts. I'll be waiting for you. Okay, attendance is already taken. Okay, I'll wait for 5 minutes. So whoever is having a doubt in which slide or something, okay, kindly unmute yourself and ask your doubts. I will send you this PPT right now. Okay, I think I can. Yes, guys, any doubts? Let me know if you have any doubts.